Okay, today in Algebra 1 we're going to be doing lesson 1.3, which is real numbers and the number line. All right. So a few things that we need to talk about. One is square root. I think we've all seen the square root sign. Okay. Now a little bit note-taking advice for you. This is what the book says a square root is a number a is the square root of a number b if a squared is equal to b. Right? Does this hold much meaning for you guys? No. Right? It might, you know, if you like that. For most of you, I'm going to say probably not. Right? I think this is probably a better one for you because it's got numbers and examples, but it says 7 squared is equal to 49. And it says, so 7 is a square root of 49. Right? So this one would be the square root. What would this one be called if that one's the square root? And just the square. Right? So that's the square, the other one's the square root. Right? Now, does anybody in here think math is really cool? Would anybody in here call math radical? All right? Depends. Well, you guys should all call math radical because of math deals with radicals. All right? Those square root symbols are called a radical symbol. The number inside is called the radicand, and all together it's called a radical. Okay? So math is radical. Now, why do you think that we call this thing right here a radical symbol instead of calling it a square root symbol? Well, that's just because I had to make my own. So, right? Have any of you guys seen a radical symbol with a number other than a 2 right there? Oh, okay. So that's why we call it a radical symbol, okay? Now, what this means here, the radical of 81, the square root of 81 means what times what is equal to 81, right? And we know that's 9 times 9. Right. This one here gives me, let's see, I'll use a nice number like 27. This one here says what times what equals 27. All right, what is it? 3, right? And this one would be 3. That's why it's called a radical symbol, not a square root symbol. Okay? Now, for us in Algebra 1, 99.9% of the time we're going to be dealing with just the square root symbol. Okay? But I just wanted to answer the question for, why wouldn't it just be called the square root symbol? It's because there's other ones. So they're called radical symbols. Now, in here most of the time, I will call this a radical. I'll call that a radical. But usually I won't call the thing inside a radicand. I'll just say, what's the number inside the square root, right? I don't really use radicand a lot, but if you hear the word radicand, right, you know what it means. All right, let's solve these two. All right, looking at part A, what is my radicand on this one? 1, okay? All right, and Eric, can you tell me what the answer to this is? 9, because we know 9 times 9 is 81. All right. Does anybody know the answer to part B? Yeah. 3/4. All right. Let's look at that and let's think for a little bit. Does anybody know how Hood there got the 3 on the top? How'd you figure that one out? Yeah. Divided by 3 on top and bottom? It's a good guess, but it's not what she did. There you go. If we take the square root sign and we say, what's the square root of 9? And we take that square root sign and we say, what's the square root of 16? 4. And then it was a fraction, right, to make 3/4. If you have a fraction that is being square rooted, you can put the square root on top and bottom. Sometimes it makes the answer a lot easier, doesn't it? Yeah. Okay. And Hood, that's what you did, right? You didn't just guess and guess right? Okay. All right, so that's problem one. We're going to talk about perfect squares. Okay. A perfect square is the square of any integer. Now remember when I did the first example we had, which was 7 squared is equal to 49. Which one was the square? 49, right? So it's the answer to a problem with a 2 as the exponent, right? And then the 7 was the what? Yeah, the square root. Right? So we're looking at numbers that have been squared. Now if I look, I may have a list here, and it starts off with a 1, it goes 1, 4, 9, 16, 25, 36, so on and so on. I have it through 100. It goes on much, much further than that. But where did I get those numbers from? Yeah. There we go. So all of these are associated with, 1 is associated with 1 squared. Then 4 has 2 squared, and then 3 squared, and 4 squared, and so on and so on. So all of these squares have nice looking square roots, right? That's why they're called perfect squares. Right? Perfect squares, because of their answers are perfect. Now let's look at 36, right? If I take the square root of 36, I get what? 6. 6 is a nice looking number, right? Yeah. Now, what about if I took the square root of 37? It would be like what, 6 point something, right? So maybe like 6.1 something, 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 right? Is 6.1 something, something, something perfect? No, it's not a very nice looking number, but 6 is. So that's how you can tell the difference between a perfect square and one that's not a perfect square. Okay? 37 can still be a square, just can't be a perfect square. All right? Any questions over perfect squares? All right. Now, this one is a question about lobsters. Now, if you look at a lobster's eye very, very closely, it looks like a bunch of little squares, or like somebody had wrapped a piece of graph paper around it. Okay, kind of like a fly's eye, but fly's eyes aren't squares; they're kind of like roundish, right? I think they're like maybe octagons or something like that, right? But lobsters are square, which means if you look very, very closely, its eyes are going to look like a bunch of squares put together like that, and it's going to be kind of wrapped around, right? So it's not a perfect sphere. It's going to have little squares in it. Some scientists measure it, and they find out that it's 386 square microns. Right. We want to know what is the approximate side length to the nearest micron. What does it mean by nearest micron? Whole numbers, right? They don't want decimal points. They don't want you to tell you, it's 2.1. They just want you to say 2. But we need to figure out what that is, all right? Now, I have 2 methods here. We're going to use them. Does anybody have any idea how we can solve this right now? Square rooting it, right? And how would you square root it? So, okay, Okay, so you're going to use a calculator, right? Oh, man, let's hide that real quick. There we go. Yeah, you guys didn't see nothing. All right, so method 1 is we're going to say square root of 386. Oh, no, what'd I do? There you go. How about 386? All right, hit enter on this. It's going to be what? 19.4 or 19.6469. Is that the answer they want? 19.64? No, what answer do they want? 20, right? So method 1, right? We said square root of 386. That was equal to 19.64, which is, what does that symbol mean? About 20 microns. Yeah, that's method 1. Using a calculator. How would you do this if you didn't have a calculator? Right? One thing we cannot do is the radical symbol with pen and paper. Right? We need a calculator to do that. So method 2 is going to be a little bit more like guess and check. Okay? Now, to find out what this is, what I'm going to have to do is I'm going to have to start by saying, well, maybe 386, maybe it's equal to about 15 squared. Right? 15 squared, maybe. So I can do 15 squared by going, 15 times 15, right, and solving it. Right. Is it 225? Is that what it is? Oh, it goes 5, 2, that's 75, 0, 5, 1. Yeah, I think it's 225. So is 225 very close to 386? No. Not really. So what do we need to do that square root of 15? We need to bring it up a little bit. How far?
4. 17.
We're going to bring it up 4 spots to 19? Is that what you guys said?
No, I meant the square root.
Oh, you would do this over here?
No, 15. Once you put the square root of 4, 72.
That's the x when you go as x change to 4.
Remember the little 2 changed to 4.
Change that to 4?
Yeah, would it make a difference?
Yeah, it would. Since these, right, this means squared, right? We're going to be changing this base number, not this number, because these are squares. The lobster's eye is a square, right? So we want to take the square root. We can't do to the 4th because of that's some weird shape. All right. So right here, let me make that a little bit cleaner. I heard somebody say 19 squared, which is nice that we already solved it once so we could guess again, but you could choose any number. If you wanted to go to 17, you could try it that way. It's just a guess and check, right? So sometimes it's going to take a little bit. So 19 squared, right? So that's 19 times 19. 19 times 19. That's 81.
361.
Oh, somebody did already. What is it?
361.
61. Okay. Now is 361 pretty close to 386? Yeah, which means, do I know it's closer to 19 than it is to 20 yet? No, so we need to do one more, and that is going to be what?
19.
Yeah, 20 like that.
20 would be 400 though.
20 is an easy one. There we go. Now we look at our original number. We look at these two numbers, and we say, is it closer to 19 or is it closer to 20? 20 a little bit, right? It's almost right in the middle, right? But we're going to say this is about 20. So I'm going to say, the answer is about 20 microns. Right? Which way is easier? Method 1, right? Can you always do it with method 1? Yeah, sometimes you won't have a calculator, so you're going to have to use method 2, right? Now, the good news is in math class, right, and here we all have calculators that we can use, so method 1 is what we're going to be using most of the time. All right? All right. Next, we're going to be talking about sets, which are a well-defined collection of objects. Okay? A well-defined collection of objects. In math, most of the time it's going to be numbers, but it can be, you can have a set of things that aren't numbers. You can have sets that aren't numbers. You can have sets of other things. Huh? Marbles. Yeah, you could have sets of marbles. Pigeons. Right? All work. The example I have here are the people in the classroom a set?
Yes.
They are. But what does a set have to be? Well defined, right? So if I just said, the set of the people in the classroom, would somebody know what I was talking about? Not really, because do they know what classroom? Do they know where to look at the classroom? No. All right. So let's try to define this pretty well, all right? So what should I change to make it well defined? Math classroom, did I hear that? Okay, people in the math classroom. There we go. Now, this is better defined, but I heard somebody say, but it could be any math classroom. Okay, people in Mr. People in Algebra 1? Okay. People in...
Algebra 1 is room, whatever room we're in.
Oh, Algebra 1 in,
In room 6, I guess.
oh, wow. In room 6. There we go. Okay? That's better. So people in Algebra 1 in room 6.
But this has room 6. Students in Sandfield.
And there we go. In Sandfield, is there other room 6s? There are other Algebra 1s, okay? So now I'm going to add to this in Stanfield. There we go. Oregon. All right? This is probably enough, right? I don't think there's a Stanfield, Oregon in Russia. All right? Okay, there might be. All right? So this is getting pretty well defined, but do you guys know what I have first period every day? Algebra 1 in room 6. Period. Oops, period. 3. Now is it well defined? What about Stanfield High School? Well, it takes care of that with the room 6, right? So room 6 has to be in the high school. What about next year? Could I teach in Algebra 1?
2011.
There we go. In 11, 12 school year. Now, was that a pain? Was that a pain doing that? Yeah, it is. Good news is, when we use sets, most of the time it's going to be with math. Math and numbers are a little bit easier to make well-defined. You don't have to go through all this, right? So math's a little bit easier to do. Right? Okay, now, talking about sets, we can talk about an element of a set, which is one object inside of the set, right? You have a set of a lot of things. If you pick one of those things out, it's an element. A subset is a group of elements inside the set. So not just one element, but a few elements that are made up from inside of the big one. All right? So if you guys get that done, we'll get a couple examples. All right. Now let's think about the set we just thought of, right? Which is all of us, right? Because we said, Stanfield and this year and everything like that. So the set. Oh yeah, it was. I'm not going to rewrite it. Xperi wrote it once, right? But it was like all of us. All right. But I'm not going to rewrite it. Well-defined. So I already did that once. Okay. Now let's think about an element of the set, okay? An element of the set. Can anybody think of an element inside of the set that we just made? A person? Which person? There we go, Hunter. Okay, he's an element, right? All of us are elements. I'm an element. Hunter's an element. Well, the rest of you are all elements too. What about a subset? Can we come up with a subset? Football players would be a subset, right? Right? So football players, there we go, football players. So everybody in here that plays football makes a subset, right? A set that's smaller than the rest of us, right? But they are set all their own. There's tons of subsets you can make. You can make subset of boys, subset of girls, subset of people taller than, 5'10". You could have subsets of people with blue eyes. You could have subsets of, people wearing shoes or flip-flops or whatever, right? You can make all sorts of different subsets. Football players is just an example of one subset. Now, after all this talk about sets, we are going to start talking about sets of numbers. And specifically, we're going to talk about the sets of numbers dealing with a thing called real numbers. Okay? Real numbers. Now, some of you might say, aren't all numbers real? You don't think so? Have you guys learned of any numbers that aren't real? What are they called? We'll learn a bit more about numbers that aren't real in Algebra 2. But for right now, every number that you have dealt with so far and plugged in on a calculator are real numbers. Okay? All right. We will talk about numbers that are not real in Algebra 2. And they're actually called imaginary numbers. So they're not fake, they're imaginary. All right? All right, now let me, here, I'm going to block this one off with a big heart like that, okay? Okay. When we talk about sets of numbers, I'm going to bring up different types of sets, and we're going to start with the smallest set and work our way out. And when we do this, it's kind of almost like a history lesson in math, and kind of the way that everybody learns about numbers too. So, when you first started learning about numbers, what did you do with those numbers? You counted on your fingers, right? And how did you count them? 1, 2, 3, 4. Natural numbers are often referred to as the counting numbers because they are the numbers 1, 2, 3, 4, all the way up to infinity. Okay? These were the first numbers that were also invented. Okay? Because of, people would be hunting and they'd see, 3 deer or something. 3. Right? So the numbers that you could count. Right? So the natural numbers are the smallest set. Okay? A set that's a little bit bigger than natural numbers, right? It's actually bigger by one number, and that number is 0. Right? These go up this way forever. Okay? So the whole numbers include 0 plus all the natural numbers. Okay? And it's weird to think about, but when these people were first dealing with numbers, they didn't consider 0 a number. Right? You either had 1 or you didn't talk about it. Right? So 0 came about after all the other numbers. Now if I look at the set of whole numbers, which is in green, you see how the set of natural numbers, which is in blue, is inside of the green box? So what does that mean? Yeah, it means that they're all in that. What vocab word would that be? So if whole numbers is a set, what is natural numbers? Subset. There we go. So each one inside is a subset. Okay? So after you learn 0 and 1, 2, 3, 4, all the way up, what other numbers do you, other types? No. No. They are integers, but what are integers? What type of numbers? There you go, negative numbers. Right? So it's -1, -2, -3, and so on. Right?
Whole numbers are inside of integers.
Yeah. So integers include the negative ones, it includes 0, and it includes all the positive ones. All right? So if integers are the set, then whole numbers are a, and natural numbers are also a. There you go. This one has 2 subsets. Yeah. Integers came after zeros, and it was invented by merchants, right? People that dealt with money, right? So if I'm going to sell somebody something, they then owe me money, right? And that's a negative value, right? So it took a while because of, is there any need to have negative numbers if all you're doing is, hunting and gathering? No. Not really, right? You're not going to talk about having negative berries on a tree or something like that. Didn't come about until money. Okay? Then after you learned the negative numbers, what came after that? And I heard somebody say it. Decimals, but there are certain types of decimals, okay? Rational numbers, okay? And rational numbers are any number that can be written as a fraction. Okay? Any number that can be written as a fraction. So somebody give me example of a fraction? 3/4, okay? 3/4. Now, does this definition say it has to be written as a fraction? Just says it can be. So also what could I put in there? 0.75. 0.75 is a rational because it can be written as a fraction. All right?
So if you write, so why would, okay,
All right. Now, integers, they can be written as fractions, right? I could have -3/1. 0 can be written as a fraction as 0 over anything. Whole numbers can be written as fractions as those numbers over 1. So they are all can be written as fractions. Now, a trick to know if a decimal can be written as a fraction or not, okay, is if a decimal ends or repeats. Okay, if a decimal ends or repeats, it's a rational number. Look at 0.75. Did it end or repeat?
No, it ended.
It ended, right? So is it a rational number?
yes.
Yeah. Can we think of one that repeats?
Yes. 0.7777.
Okay, I'm going to come up with an easier one first, and then I'll come back to 0.7 repeating, okay? Yeah, the 0.3 repeating, right? 0.3333333. It's 1/3. Right? So can 0.3 repeating be written as a fraction?
Yes.
Yeah. And 0.7 repeating can be written as a fraction. Does anybody know what fraction?
7 over
Close by thinking there's a 7 in there. There is a 7, but 7 goes on top. The bottom is 9. Right? Just from memory of seeing it. Right. Actually, there's a trick with these fractions here. And I'm going to go forward a page and then I'll come back. So 0.1 repeating is equal to 1/9. 0.2 repeating is 2/9. What's 0.3 repeating? Yeah, it's 3/9, but reduces to 1/3, and it goes on through all of them. Yeah, this would be the simplest form. Yeah. Ooh, okay. So we go down through all of them. 0.9 repeating is equal to 9/9, which simplified is 1. So 0.9 repeating is actually 1. Good. All right, now I'm going to go back. All right. So rational numbers are any number that can be written as a fraction. They're decimal. Excuse me. They're decimal. They have to end or repeat. With the repeats part, it doesn't have to repeat a single number like 0.3 down here or 0.7 repeating right there.
like 385, 385, 385.
Yeah, like 0.385 repeating, which would be 0.385, 385, 385, would have a fraction. I don't know that one off the top of my head. Right? But an example of one that I do know off the top of my head is 1/7. Okay? 1/7 is, let's see if I can remember it all the way. I think it's 0.145628. So it repeats 6 numbers, right? And then it repeats, and it'll go 1, 4, 5, 6, 2, 8 again, right? So does this one repeat one number? Does this one repeat one number? It repeats 6 numbers, but is it still a fraction?
Yes.
Yeah. Now, if this side has numbers that can be written as fractions, right? What's the other side going to be? Yeah, and if we think about it, it has to be written as a decimal that does not end and does not repeat. What number is that? There's a famous one. Never ends, never repeats. Well, infinity is not a number. It's just... There we go. It's pi. So I'm going to move my heart over here.
5. It never, what?
Pi never ends, never repeats. Okay?
5 doesn't.
All right. Does anybody know any other ones? Let me ask you guys. Infinity, which is a sideways 8, does not count as an actual number. It's like a limit. All right. All right. Another one is E.
Okay, I know this is bad.
E deals with interest and accounting. Okay. Now let me ask you guys something. Which set do you think is bigger, irrational numbers or rational numbers?
Rational numbers.
You guys are all wrong. They're the same size. Yep. Between every two rational numbers, there's one irrational number. So if you get down to little tiny decimal points, it goes rational, irrational, rational, irrational, back and forth. All right. Now let's think about irrational numbers, right? And they're both infinity. Okay. They'll both have an infinite amount of sides. Right? If we think about irrational numbers, right? Pi is irrational. What about pi plus 1? Is that irrational?
Well, wouldn't it, you'd still have the decimals.
Yeah, it'd just be 4 point, right? And then all those decimal point, right? So then you could also have pi plus 2, pi plus 3, so there's a lot of those. Square roots of any number that's not a perfect square is irrational, right? Square root of any number that's not a perfect square is irrational. So 2, 5, 6, 7, 8, 10, 11, 12. Try not to say some of them.
14.
All right. Yeah, square root of 14. Those are all irrationals. So there's going to be a lot of them.
Any good time that no one is gonna skip it.
Okay. So those are all of them. Now, let me look at irrational numbers and rational numbers. Is one a subset of the other one? No. Is one written inside of the other one? No, so they're separate sets. Okay? They're not subsets, they're separate sets. Oh, that was what I talked to you guys about. All right. Now, knowing the subsets, right, of real numbers, which number does each one belong to? All right? 15. Which subset does that one belong to? Even smaller than whole numbers. There we go, natural number. It does belong to the whole numbers, but I want to get the smallest ones, right? So this one is natural numbers. How about B, which is negative 1.4583? Is it integers or rationals? Rationals, right, because it has a decimal place. And does the decimal place end or repeat? Yeah, it ends. So this is rational. And square root of 57. Irrational. Why? Yeah, it's a radical of a number that's not a perfect square. So this one's irrational. I don't know why I wrote 2 capital letters on that one, but I did. All right? I guess so. Irrational. Right? Oh, and one part that I kind of forgot to talk to you guys about are all of those sets, when you add them together, right? The rational and the irrationals, when you add them together, you get real numbers. So all the numbers together are called real numbers.
So all of them separate are imaginary numbers?
All of them separate are subsets of real numbers. But you have to have them all together to make. All right. Inequalities. Okay. Inequalities. Now, I guess that you guys have all seen these numbers before, right? Or these symbols before, right? Less than, greater than, less than or equal to, greater than or equal to. How can you tell the difference between a less than sign and a greater than sign?
The less than what?
There we go. That's the trick. So if you have troubles remembering, the less than ones, right, are the ones that look more like L's, right?
That's how I figure out left and right.
Well, yeah.
But yeah, but if you're looking at a greater than sign, does that look at all like an L?
No, you drew it different.
The L? So well, I'll put this L over there. Does that one and that one look the same?
No, you're right.
Yeah. So it's almost like a backwards. It's like an L and a backwards L.
You make the other one point out more.
I'm sorry. All right. All right. So moving on, and we use them to compare values, right? Tell size differences. So here I'm going to use an inequality to compare these two. So I have square root of 17. I'm going to put a value there, and we have 4 and a third. All right? Do you guys know which one's bigger right now?
Yes. 4 1/3 is the square root of 7.
You guys know 100% sure? Which one's bigger? Now, what would make it really easy to compare them? Use a calculator and do what with it? Make them decimals? Okay. So first off, what's 4 1/3 as a decimal?
4.13.
There we go. I knew you guys knew that one. 4.3 repeating. What's square root of 17 as a decimal?
It has to be 4 point something.
It has to be 4 point something.
It's 4 times 4 is 6.
Yeah. So we know that's got to be 4 point something.
4 point something.
Did you use a calculator? There we go. Okay. 4.1 something something something, right?
So it's that side.
Which side's bigger?
Purple.
All right. And then which symbol am I going to have to put in there?
Square root of 17. The greater than.
A greater than?
Less than. No, wait. No, for the 20 for people.
Point.
So less than.
So
Sorry.
a less than like this, right?
I know.
Okay. And I'm going to erase this blank so it doesn't look like an or equal to. There we go. All right. So we have a less than symbol like that. Okay. And if you have troubles remembering which way this points, what's the trick?
The alligator eats a bigger number.
Yeah, alligator, right? Eats the bigger number, right? There you go. We have an alligator. There you go. An alligator eats a bigger number, right? I've heard that some teachers teach it as a shark will eat a bigger number, right? That doesn't count. It's always an alligator, okay? So if in your mind you're thinking sharks, get rid of it. Think alligator, or else you're going to get all your math wrong. You'll be hard. Yep, less than's an L. Okay. Okay. Stick with me. We only have a few minutes left. But problem 5 is we're going to be ordering these from least to greatest. Okay. This is last problem we're doing together. Okay. So we want to order them from least to greatest. What would make it easier to order them? Well, we're not putting stuff away yet. Decimals, okay? So what's the square root of 4 as a decimal? There you go, 2. Then we have 0.4, that's still a decimal. How about negative 2/3?
Negative
0.6 repeating. Square root of 2?
1. No, it's 2. It's
Negative
0.
How could we figure that out?
by square root.
There we go, calculators. I'll leave that one blank. The last one's 1.5.
Why is it negative? Oh.
I
I just see that.
1.414.
You're alright. You look like you're in pain.
Okay, there we go. Now let's order them from least to greatest. So which one's the least?
Negative 0.6. No, I'm just kidding.
Negative.
I know that the 1.5 almost looks not, but I forgot the. Right, I didn't hit the enter sign soon enough, so that was my fault. Then what's the next smallest?
Negative 1.5.
Negative
No,
0.6
yeah.
1.4.
Then what's the next one?
1.4.
0.4. The next one?
1.1.
And then 2. Okay, now. Excuse me. This is completely right in order and everything, but if you're taking a multiple choice test or on the state test, the answer's not going to look like this. What is the answer going to have?
How they have it.
Had it. So negative 1.5 was negative 1.5. Negative 0.6 was
Negative 2/3.
0.4. Well, they had 0.4, right? And then what was this one?
Square root of
Square root of 2, and then we had square root of 4, right? Okay, good. Write down your homework, okay? You should have a little bit of time tomorrow to work on it when you finish your test. But other than that, we might work on this as our warm-up on Wednesday. This will be due Thursday. Okay, due Thursday. All right.